Hi, my name is Julian. Welcome to the presentation of our paper. Hemodynamic quantities in blood vessels are a helpful tool for treating or preventing cardiovascular disease. For example, low and multidirectional wall shear stress have been found to correlate with plaque development and artery remodeling. The figures show plaque progression in areas with low, medium and high wall shear stress and the correlation of wall shear stress with different kinds of plaque. Such biomarkers help clinicians decide for appropriate treatment, for example, stent placement, etc. An exemplary method to quantify blood flow and obtain hemodynamic parameters is 4D flow MRI. However, since it's not widely available and may be less accurate on small blood vessels, computational fluid dynamics is the method of choice for most. The method boasts high accuracy and accessibility to readily available commercial software. On the downside, sufficiently accurate fluid simulations require a lot of computational resources and simulation time. In some medical applications, high-precision solutions may not be necessary and can be traded for evaluation speed. To make use of hemodynamic biomarkers in this domain, surrogate models are needed. Deep neural networks are an attractive class of surrogate models because once they are trained, estimations can be really fast. To employ them in hemodynamic parameter estimation, we generate large datasets of ground truth simulations using CFD and optimize a network's parameters in an offline training phase. Inference then only takes a single forward pass through the network and is performed in seconds. Most existing approaches to employ deep neural networks in hemodynamic parameter estimation rely on a handcrafted parameterization of the geometry to extract relevant features that can be used with a convolutional neural network. This approach has been shown to yield good results for certain problems, but limits the scope of the method since the chosen parameterization might exclude certain classes of blood vessels. In this work, we propose to use graph convolutional networks and let the network learn its own latent parameterization directly from a surface mesh, as well as predict hemodynamic vector fields conveniently on the same mesh. State-of-the-art graph convolutional networks, or GCNs, consist of layers that perform convolution in the form of message passing, which I will sketch in the following. A CFD mesh consists of vertices and polygonal faces which induce a graph with vertices V. We use this graph to define our graph convolution. On every vertex P in the graph, we define a C-dimensional signal f. F is usually high-dimensional intermediate layers, but can also represent a physical or geometric quantity, for example, XYZ coordinates. Graph convolution aggregates information from a neighborhood N around vertex P by linearly combining signal vectors and multiplying them by a convolutional kernel K. This is called message passing. This equation here covers multiple forms of convolution by appropriately specifying ρ and k. For example, we can choose an isotropic kernel, which means a constant matrix that does not depend on the neighboring vertices. Every vertex in the neighborhood is treated as equal by this kernel. Furthermore, choosing ρ to be the identity matrix leads to the popular graph sage layer. If we choose ρ to be a learned neighborhood attention mechanism, we arrive at feature-steered or for short feast convolution layers. Since different neighboring vertices are here treated differently, this is an anisotropic convolution filter. Anisotropic filters are more expressive than isotropic ones and can pick up on patterns more easily. Thus, what we ideally want is an anisotropic kernel K to go along with the anisotropic ρ. We realize this by so-called gauge equivariant mesh convolution. The premise of gauge equivariant mesh convolution is that in order to perform anisotropic convolution, we must first define a local coordinate system, we also called gauge. This is done by projecting the neighboring vertices on a tangent plane and arbitrarily picking a reference neighbor that together with the plane normal spans a coordinate system. The convolution is then computed by linear combination of the signals f in this gauge, where ρ prepares the signals for combination by expressing them in the same gauge. Finally, the result must be mapped back to the mesh to update the vertex signal at P. The choice of gauge was entirely arbitrary here, so we required a convolution operator to yield the same result no matter the gauge. This can be achieved by designing the convolution to be gauge equivariant. Gauge equivariant mesh convolutional neural networks, short GEMCNN, possess the neat property of being equivariant to rotations in 3D space. Given an input mesh, our GEMCNN predicts a 3D vector field with one vector on each mesh vertex. Rotating the mesh and using that as an input to the GEMCNN will produce an accordingly rotated prediction. This is due to a combination of vertex normals being equivariant under mesh rotation, as well as the network's message passing being defined strictly tangentially to the mesh surface. Even though this might seem trivial, current state-of-the-art graph neural networks do not possess this property. We take our convolutional layers and form residual blocks which contain two convolutions and a skip connection. These are cascaded in a 3-scale architecture similar to the well-known UNet. Pooling is implemented by computing a hierarchy of vertex subsets using farthest point sampling and establishing scale correspondences by geodesic nearest neighbors. Input features to the network are constructed by linearly combining relative distances and vertex normals. Additionally, we supply the network with the notion of geodesic distance to the artery inlet. This is necessary since otherwise no blood flow direction could be inferred from the geometry. To put our method to the test, we randomly synthesized a dataset of 2000 idealized artery shapes. These shapes are symmetric to the XZ plane and have up to 2 stenoses of varying degree. The shapes were meshed with mesh size refinement proportional to the vessel radius and 5 tetrahedral boundary layers. We then simulated blood flow in these artery models using CFD. We assumed rigid walls, constant uniform inflow, and a weakly applied pressure at the outlet. To make things interesting, we also synthesized 2000 bifurcating artery models, modeling the left main coronary bifurcation. All of those consist of proximal main vessel, distal main vessel, and side branch, with all angles and radii sampled from an atlas of empirical coronary measurements. In contrast to the singular artery models, the bifurcating artery models were not constricted to a certain plane or symmetry, but freely followed the distributions found in the atlas. This time we applied a parabolic inflow boundary condition. The synthesis and simulation of both datasets was automatized using the SimVascular Python shell. For experimental evaluation of our method, we trained 3 deep neural networks consisting of graph-sage, feature-steered, and gauge-equivariant mesh convolution layers. Each of these had roughly 800,000 trainable parameters, and the CFD simulations acted as ground truth. What you see here are the input mesh and the training label of a sample that the networks have not seen during training. Outputting a prediction takes the network just under 5 seconds. Even though this is a particularly challenging example, the wall shear stress heat maps looks reasonable. Zooming in and visualizing the wall shear stress vectors at every vertex reveals where the neural network was struggling, but also that it succeeded in correctly predicting the flow vorticity and multidirectional wall shear stress. The same holds true for the bifurcation models. In this study, we chose to not fine-tune our network specifically for the bifurcating artery models to highlight the general applicability of our approach. This table here shows a quantitative evaluation of our network's performance. We report the normalized mean absolute error and the maximum difference between ground truth and prediction evaluated on a held-out test set, which the networks did not see during training. In order to quantify the equivariance property of the GemCNN, we let all deep neural networks make new predictions, this time on randomly rotated test samples. Both SageCNN and FeastCNN predict complete rubbish, as indicated by the high error metrics. GemCNN retains its accuracy. This property could be beneficial in applications where data is difficult to come by. The SO3 equivariance improves data efficiency by liberating the network from having to learn spatial orientation. In conclusion, we have shown that graph and mesh convolution neural networks are feasible for CFD surrogate modeling for hemodynamic parameter estimation in coronary artery models. We propose a plug-and-play method that operates directly on the CFD mesh and thus can be substituted into every workflow that previously used CFD. Our method is powered by anisotropic graph convolution and is able to easily predict 3D vector-valued quantities, all while staying equivariant to rotation. Our future research in this line of work will aim to condition the networks on patient-specific user-supplied boundary conditions, which include pulsatile blood flow. Furthermore, we will try to step away from synthetic data and evaluate our method on realistic patient samples. Thank you very much for your attention. If you're interested in our implementation of the deep learning framework, you can find it on GitHub. If you want to download these slides, you can do so by scanning the QR code with your smartphone.